In this video, I'm going to talk about inverse functions. Given a particular function, the inverse function is simply the undo button of the original function. What does that mean? Let's take a look. For example, we have a function f(x) is equal to 2x. This function simply doubles every input. In order to undo this action, we should halve our input. So the inverse function of f, written as f superscript -1 of x, should be x over 2. A slightly more formal way to define this undo property is by using composition of functions. What does that mean? Well, if we take f and then compose with f inverse and act on the input x, then this is defined by f acting on the output f inverse of x. So composition of functions simply mean that we perform function actions one after the other. Since inverse function and the function itself undo each other, after you perform the function inverse and then you perform the function, they should cancel each other's effect and get back our original input x, as if there was no action on the input x at the first place. Let's try to illustrate that using these two examples. F of f inverse of x. Evaluating f inverse of x, we get f of x over 2. And we should plug in x over 2 into this x to get 2 times of x over 2, which simplifies to x. So we now see that f of f inverse of x is indeed simply x. On top of this relation, we also need to make sure that when f inverse composed with f in the other order and acts on x, we will also get back just x. Once again, composition means that you have f inverse acting on f of x. Back to this example, we have f inverse of f of x, which evaluates to f inverse of 2x. And then we need to plug in this 2x into this x to get 2x over 2 and simplifies to x. So we once again see that f inverse and f cancel out each other to just get a simple output x. These two combined is what we truly mean by the undo property of an inverse function. It is extremely important to recognize that not every function has an inverse. So now the question is, what kind of function will have an inverse? For a function to have an inverse, we have to make sure that no two inputs lead to the same output. Why is that important? Well, let's say we have a function f that has an inverse, but at the same time, f of 1 is actually equal to f of 2. Then plugging them into the function inverse, we will still have the same output. However, from the undo property from the last slide, we know that the left-hand side is 1, while the right-hand side is 2, which leads to a contradiction. Therefore, no two inputs could ever lead to the same output if you want to have an inverse function. An equivalence condition, but a more visual way of saying this, is that the graph passes the horizontal line test. The horizontal line test says that if every horizontal line passes through the graph at most once, then this function has an inverse. Why are these two conditions equivalent? It is because if we have two different inputs on the x-axis that lead to the same output, then there is a horizontal line that passes through this graph twice. Let's use these two conditions to check whether some functions has an inverse or not. For example, I have my function f from R to R such that the function action is given by 5x squared minus 17x plus 64. This is a quadratic function, and the graph is always a parabola. A parabola will fail the horizontal line test because many horizontal lines will pass through the parabola more than once. Therefore, this function has no inverse. Another function that has no inverse can be given by the following. G of x is equal to the square root of x minus 4 to the power 8 plus 3 times of absolute value of x minus 4 plus 29. This time, I have no idea what the graph of this function looks like, but I'm not going to worry about it. Rather, I'm going to plug in x is 5 and x is 3 into this function and try to see what their corresponding outputs are. G of 5 would look like this. Square root of 1, because 5 minus 4 is 1, plus 3, because 5 minus 4 once again is 1, plus 29. While G of 3 will be square root of, once again, 1, because 3 minus 4 is negative 1, but raised to the power 8 will give us positive 1, plus 3, because 3 minus 4 is negative 1, but absolute value will give us positive 1, and then plus 29. They are the same numbers, so we have two distinct inputs that lead to the same output, and hence this function g has no inverse. To quickly summarize, there are three statements about a function f that look different but are actually equivalent. The first one is that f has an inverse. And the inverse function is always written as f with the superscript -1. Please note that we would not call this power -1 because it's not really a power, but just a notation. The second one is that the graph y equals to f of x passes the horizontal line test. The third one is that the f is 1 to 1. This is an adjective describing the property that every one input will lead to a unique output. You would never have two distinct inputs leading to the same output. So we will say f is a 1-to-1 function. Before we end this video, we would like to point out that if a function f is not 1-to-1, we can sometimes change the domain to modify the function so that it's now becoming 1-to-1. For example, if we have f from R to R such that fx is equal to x minus 2 squared, then the graph of this function looks like the following. It is a parabola with the vertex at x equal to 2 and it is opening upwards. If we change the domain so that it is now from -∞ to 2, then this new function will be one-to-one, even though the action is identical. Why? Because if we take this to be our new domain, then we are only including all the number from negative infinite up to 2. And hence, the graph of G is now only this branch. This branch will pass through the horizontal line test, and therefore this is now a one-to-one function. There are many other ways to change the domain to make this function into a one-to-one function. For example, I could choose my h so that the domain is now from 3 to 4 as an open interval going to R, such that hx is equal to x minus 2 squared. This particular domain means that we are only taking this small interval from 3 to 4, and the corresponding graph also passes the horizontal line test. However, this way of modification is more important because this function keeps the exact same range as before. The range of f is from 0 to infinite, while the range of g is also from 0 to infinite. In the next video, I will talk a little more about some other properties of inverse functions, as well as how to find the inverse of a given function. Thank you very much for watching. If you like this video, please subscribe to our channel and we will learn more fun math together. Thank you.